Okay, so one quick brief announcement. The new homework for chapter 42 is now posted. You have about 12 days to do it. It is a long assignment. There's 12 problems, some with multiple parts. So I suggest that you start early. It's going to be a long one. And then we'll have a final one on semiconductors when we get to that section, which will be due on the last day of class, essentially, right before finals. You can always do them early. That's fine. You don't have to wait until May 3rd or May 2nd. Okay. Any questions before we start? Like on anything we've done up till now? I'm going to do a little bit of a detour from the end of the last class. We started getting into the wave functions of the hydrogen atom, but I thought that it might be useful to come on up and sign in. I thought it would be useful to go over some of the energy, with the quantum numbers, the energy levels, and the multi-electron atoms. And to do that, I think I'll probably need this other board here pulled down. Probably need to refer to the periodic table occasionally. But what we're going to do is, first we're going to review the material on the hydrogen atom that we talked about last time, and then we're going to extend that to multi-electron atoms and some of the properties that are associated with them that occur in the periodic table. So let me begin by talking about the hydrogen and a repeat of what we talked about. So for hydrogen, we have energy solutions. So we have allowed energies for allowed energies, E values for the electrons in hydrogen, which is basically one proton, right? And because the proton is so much more massive than the electron, we can consider that as a stationary object, and the electron whizzing around it, similar to the pattern of the planets in their orbits. Okay, so there were two things that came out of the Schrödinger equation. This came from the Schrödinger equation, and there was also two other properties related to angular momentum that came out. So let me just review those very briefly. What the upshot or the conclusion of this long Schrödinger equation for the electron in a potential well, and remember the potential well for an electron is the Coulomb 1/r potential that one has for a charged particle, and I believe I forgot to put it in. Z is the Z of the, if I were, well, Z for hydrogen is 1, but let me just write this out, E squared. Right? So, of course, for hydrogen, we have Z equals 1, and so we will just evaluate this as we go along. Okay, well, the upshot is, as we know, that the total energy E is equal to kinetic energy plus potential plus U of R, where R is the radial distance away from the orbit. And these allowed energy values are quantized in such a way that the E sub n is equal to minus 13.6 electron volts divided by n squared. And because we may actually be dealing with heavier nuclei with a Z of the nucleus, which corresponds to the number of protons. So where Z is called the atomic number, and that's equal to the number, which is equal to the number of protons. So this is equal to the number of protons, right? And we'll talk initially by what we, if we're talking about a atomic number Z, initially we'll be talking about single electron atoms. So this will still be one electron in orbit, or quote in orbit, because quantum mechanically they don't really orbit in the sense that we think of a particle orbiting. It basically is described by a wave function. And the wave function tells you what the probability of where it is. It doesn't tell you that it's moving. We can calculate its average speed and its average radius and those properties, but it's not a precisely defined quantity, and it's limited by the uncertainty principle. The uncertainty principle says that we cannot know precisely its velocity and its position at the same time. We may give an example of that as we go on, but for now, I want to review what the outcomes were for the energy levels and the angular momentum. And the second thing that came out of the Schrödinger equation was that the angular momentum is quantized, and I can either write it as squared or just L, but L squared is equal to L times L plus 1, and this is equal to h bar. And also the Z component of angular momentum is quantized, and that's equal to m sub L times h bar. Right? And furthermore, there are restrictions on these integers. N, of course, can be equal to 1, 2, 3, all the way up to infinity. Notice that as n goes to infinity, E goes to 0, right? Because I have a negative number for the total energy out front, which means that the particle, the electron, is bound in its orbit. It has these particular values, allowed values, and there are also allowed values of the angular momentum. This is called the orbital angular momentum. Orbital angular momentum, and it has the quantum number L, and L is also constrained, and this falls out of the Schrödinger equation, which right now we're simply giving you results. It generally takes 5 or 6 hours to solve this differential equation in class. It's at least 2 weeks worth of work to actually solve the equation and come up with this, so we're giving you the Cliff Notes version of the problem. Unless you're a physics major, you'll never have to see that part again. So the result of these integer values that come out is that L has to be less than or equal to n minus 1, and it has to be greater than or equal to 0. So L has to fall within these regions, and these are the allowed values. It is bounded above by this is called the principal quantum number of the atom. This is the principal quantum number. And this is called the orbital quantum number. And then, of course, this is the Z component. This is the Z component of angular momentum. And of angular momentum. That's my symbol for angle. And these values are also quantized. They're quantized in such a way that they are integer values where m sub L has to be less than or equal to L and greater than or equal to negative L. And so these are the conditions on the quantum numbers that exist for a electron in orbit. So we can draw a picture again. We did this last time, but we'll draw it again. We said there's a 3-coordinate system axis, x, y, and z, that we use to describe the motion or the wave function of the electron in its orbit around the nucleus. The nucleus has charge z times e squared, z times e. And we are using the notation, as we will be, is when I refer to E, what I really mean is the absolute value of E, okay? So my value of E is the absolute value V, which is 1.6 times 10 to the minus 19. If there's a negative sign, I will put it explicitly in there so that you can keep track of that. So the idea is that if we think of orbits, which we said is only an approximation to the truth, then I can, as I drew last time, I can have a proton zipping around the nucleus, and it's at some radial distance r, and we actually use the angular momentum vector r cross p to calculate the angular momentum in quantum mechanical sense. But the answer that comes out by using this is that the angular momentum is quantized and the z component is quantized. Now the x and y component are not quantized, and by the way, so if I were to draw the L vector, I would draw it right here, and there's the angular momentum, r cross p, and the z component, we did this last time, was quantized, right? So this is L sub z, and it can only have fixed values, and so we gave an example that it can be at this angle, it can be at this angle, it can always be at angle 0, with 0 z component, and then it's symmetric about in the negative z direction, it can have negative z components as well. Now, we also said that without some external reference, I cannot tell you what direction x, y, and z are actually in. Right? I can imagine that z is perpendicular to the Earth's coordinate like this, right? But any atom that is oriented in a way where its angular momentum z component is quantized this axis can later tumble in a gas, and it moves around in a gas. And now z component can be anywhere, right? So z really doesn't really have a geometrical meaning in space unless I find a way to define the z-axis. And we'll talk a little bit about that later, but give you a precursor that typically what we will talk about towards the end of the lecture is that I'm going to apply a magnetic field B in the z direction, and this will be what we call B sub z, right? So now I have an external reference, and I can show you some real effects that come out of angular momentum. The other thing that is important is that, notice right here that the energy level does not depend on L, does not depend on angular momentum. On L or M sub L, right? It only depends on the principal quantum number n. So I can have multiple angular momentum states associated with any one principal quantum number. And so remember, this is the same principal quantum number that we use to describe the orbitals, right? So in the orbital pictures, when we were describing the transition of the electron between orbitals and the emission of light, when, for example, it drops down from the n equals 3, let's call this E3 level, down to E1, then I can get, of course, light being that's emitted with frequency times F, which is equal to the E3 energy minus the E2, minus the E1. So in this case, it would be E3 minus E1. Okay? So this is the meaning of the quantized energy levels. It's convenient to think of them as occurring in increased radii, but of course their radii are not really fixed. It's only a conceptual background to kind of think about it, to help the concept. Any questions so far? We want to stop and if you have anything you want to add. How many people have seen this before? Nobody? Nobody has seen the angular momentum for hydrogen. Okay. Anybody familiar, let's say, with the idea of orbitals? Or orbitals, there we go. Chemists always talk about orbitals, right? When they talk about orbitals, they are talking about orbital angular momentum states. Right? The electron can be, for example, in an L equals 1, L equals 2, or maybe an L equals 3. Those are different angular momentum states. Those are different orbitals. So different L values correspond to orbitals. This is what the chemists talk about because when they're talking about binding of different atoms together, they want to look at the orbitals of the electron. And the different L values are then referred to in that context. Keeping in track, of course, that the angular momentum L max, so L max is always, the maximum value of L is always n minus 1. So an electron can be in different angular momentum states, and it can jump around. So when we have electrons in n equals 2, for example, they can be in a angular momentum L equals 1, or they can be in angular momentum L equals 0, or they can be in both. Yeah? They can be one or the other, or they can be in both. That's a more sophisticated concept about that, but basically, if you want to think of them as jumping, they can jump between those. There's no energy difference to suggest that they can't be in one or the other. Generally speaking, if an electron is excited to a highest energy state, it will decay back down to its lowest energy state. Right? And so things will always stay as close to the nucleus. Electrons will always stay as close to the nucleus as they possibly can. Now, so let's ask the question for a given L, for a given L, how many, for a given N. Let's replace that. For a given N, principal quantum number, how many L and M sub L values are there? And by the way, the way we talk about this is that we say that electrons with different quantum numbers are in different states. So if I have a particle or an electron in the, let's say L equals 1, M sub L equals -1, then it's in a different state than a particle of L equals 1 and M sub L equals +1. So the different quantum numbers are associated, are in different quantum states. So we refer to the state of an electron as different states. We refer to the state of an electron as specifying its quantum numbers. Right? And so depending on what quantum numbers it has, it'll be in one state or the other. It's kind of like, when the president gives a State of the Union, right? He's going to say, what is the state of the economy? What is the state of our foreign policy? What is the state of going to war, peace? Those are all things that characterize the state of our union. In the state of electron, those things are these quantum numbers. So we call those states. And, as we've seen with the handout, there is a probability function, psi, of r, theta, and phi, that's associated with those quantum numbers. And remember, there was n and L, so n to move, which is right, this is psi. But you remember that we wrote this as a product of separate functions. The radial vector component depends on n and L. The angular components, which are called spherical harmonics, because they were actually studied for other areas of waves, such as sound, that they can be described by the other two quantum numbers, m and L. And this is the what we call the state. The state. This is the state also, right? So we can refer to the state by its wave function, or we can refer to the state by its quantum numbers. Okay. So back to our question. For a given number n of the quantum number, electrons in a certain n quantum state, how many L and M sub L values are there or can there be? Well, we are going to solve that. We're going to use these two conditions, namely that L has to go from 0 to n minus 1, and M sub L can go from minus L to plus L. And of course, they all have to be integers. Okay? So, what should be clear to you from this is that there are 2L plus 1 values of M sub L. There are 2L plus 1 values. Everybody see that? If M sub L goes from minus L to plus L, then for every L I have a minus L. For every positive integer I have a negative integer, and I'm going to count down from L down to 1, and then there's one value of M sub L in the middle, which is 0. So I get the value, that additional state comes in for the 0 state. I'm seeing some blank looks, so make sure you understand that. If I have a sequence of integers that goes from minus L to plus L, there are 2L plus 1 possible values. Everyone see that? Okay. I go from minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3. There's 7 values. Okay. Minus 2, minus 1, 0, plus 1, plus 2. There's 5 values. Okay. That's for L equals 1. Or L equals 2. Yeah, L equals 2, there'll be 5 different values of M sub L. L equals 3, there'll be 7 values of M sub L, and so forth. Okay? All right. Now, then clearly, if I want to find out how many of these different values are possible, then the number of states for a given L, for given N, okay, is equal to the summation of L equals 0 to N minus 1, because this is the maximum value of L. This is the maximum L, and for each one of those terms in that I'm adding, I have 2L plus 1 values of M sub L. So the number of value of possible states, meaning this is the number of L and M sub L values, is equal to this number, and mathematicians have worked this out for us, so we can write it very succinctly. It's equal to n squared. Right? Right? So as you might expect, as the number n goes higher, I can accommodate more angular momentum states, but I can also accommodate more M sub L states. And as the number n grows higher, the series can be proven to be equal to n squared. So there are every quantum state n, for each quantum state n, for each n, there are n squared. They're n squared states. We call it states available, or quantum number, unique quantum number combinations. Right? So for each value of the principal quantum number n, there are n squared values of L and M sub L. Right? So that's how many states are involved. Now, in the single electron atom, the only thing that, of course, the energy affects the energy is the value of n, not the value of L. If I now go, and we'll talk a little bit now about the multi-electron atom. If I go now and I add a 2-electron atom, so let's suppose now take a very simple basic example. Let's suppose we talk about the helium atom. And for the helium atom, I have Z equals 2, there's 2 protons, and I have 2 electrons, right? Now, one way I can characterize this is to say that there's 1 electron that is in the n equals 1 state. Well, there's actually 2. There's n equals 1 here. And there's another one which is also in this state as well. And because n equals 1, we know that L is equal to 0, right? Because L max is n minus 1, and therefore the only state that's possible is the L equals 0. We'll come back, we'll keep going, okay. So now I can go to, so for example, this might be one in which there are 2 electron charges, or Z is equal to 2, let's write it another way. The nuclear charge, this would be equal to 2 times the electron, and it's a positive charge in the nucleus. And by the way, if I was dealing with helium, then I would have to calculate its energy levels differently. I would have to say that E1 is equal to minus 13.6 eV times Z squared, so this would be times 2 squared. And E2 is going to be equal to minus 13.6 eV times, I'm sorry, E2, I did that wrong. I'm sorry, this would be 1 squared. So, no, 2, I'm sorry, 2. I did it right. Oops. Well, I'll keep doing it again. This part's right. Now I'm going to divide this by n squared, which is 2 squared. And I'm going to multiply this by 2 squared, because this number is minus 30. You're going to hear this so many times, this number shall be burned in your brain. And it's just evaluating the coefficients in the Bohr theory, in the Bohr equation, and for the energy levels. And this is Z squared over n squared, right? Z squared over n squared. So this would be, for example, this would be equal to minus 54.4 eV. This one is equal, this energy level for helium is minus 13.6 eV. This energy level, E3, would be, I still keep the 2 squared here, but now I divide by 9, so this is divided by 3 squared, minus 13.6 eV, and so on, right? You can calculate all the energy levels, and I can do this for Z equals 3, and I can do it for Z equals 4, et cetera, et cetera. Okay. So this is the basic idea of what we have. Like so many few people here today. Just notice how empty this place looks. Weather must be getting nicer. Okay. Okay. So anyway, these are the energy levels that we can calculate for this. Now, I can go on and I can add more electrons in here. And if I didn't know better than what I know now, then I would say every time I add an electron, I'm just going to keep putting it in the n equals 1 state, because they're going to go to the lowest energy state anyway. And unless they collide with each other, they'll all go there, right? They'll all go to their lowest energy state. But then there were some problems with that theory, and particularly the wave functions and the energy levels don't match up if you put them all in their lowest energy state. So another famous physicist that you've all heard about was named Wolfgang Pauli. Does anyone know what Wolfgang Pauli discovered?
Electron spin.
Well, that too, yes, both, right. Correct on 2, Ken. Electron spin and the Pauli exclusion principle, both of which we're going to talk about. But the first one was the exclusion. Yeah. So the Pauli exclusion principle said that Pauli exclusion principle, right? The Pauli exclusion principle says that no 2 electrons in an atom can occupy or can have the same quantum numbers, can have the same set of quantum numbers. Right? And spin angular momentum is exactly what you might think it to be. Namely that the particle spins on its axis. We know, for example, that just like the Earth has its orbit around the sun, which is like the electron orbit, the Earth is also spinning on its axis as it goes around the sun. So this orbital angular momentum, or this spin angular momentum, I'm sorry, is another property that was discovered and was confirmed. And it turns out that it is also quantized. Now, there's several ways to write angular momentum. I mean, we can write it as r cross p for an object of, we can also define a quantity called the moment of inertia. Has anyone ever heard of moment? Do you get that in physics, mechanics? The moment of inertia is equal to m times r squared, where r is the distance also from the center. And I can define the angular velocity omega, which is equal to the ordinary velocity divided by the radius. Right? And this is given in terms of radians per second. That's why it's called the angular velocity. Similar to actually our wave equations. Remember when we wrote sine kx minus omega t. Omega was an angular velocity, much similar to this. So we can write then that this is the I, and this is now for an electron, right? So we're going to talk about electron spin. And even though the electron doesn't have a radius, we can define something which I will call RC, classical, right? It's called the classical radius of the electron. And the angular momentum for a spinning, or for a spinning object, I can show that these two is equivalent to I times omega. So I omega, moment of inertia times angular frequency, is very much like linear momentum, right? Which is mass times velocity. Only here, the angular definitions of speed occur, and the mass is replaced by mr squared. So this is equal to mr squared times omega. Okay. All right. Now, to actually calculate, that's for a point object that's moving around at a radius r from the center of its motion, like the electron in orbit. But here, the mass is distributed, spinning on this axis, so I have to do an integration or an integral to actually calculate the angular momentum of the spin of electron. I mean, I do know its mass, right? We do know that mass is equal to 9.11 times 10 to the minus 31 kilograms. And I can, of course, we don't usually use those units, but, and I can give you a number for the classical radius, and I can calculate this number, okay? But I'm trying to tell you the intuitive concept of spin, which is basically exactly how we would normally think of spin, right? Okay, in quantum theory, this quantity, this spinning momentum, is given a special L, is given the symbol S, which are equal, okay? In other words, the definitions are equal. But the spin, and I'll write simply, the square of the spin vector is equal to S times S plus 1. Is equal to S times S plus 1 times h bar squared. And the z component of spin is equal to, and by the way, for electrons, S is equal to 1/2, period. There is only one quantum number S for the electron. Okay? And this gives you the amount of spin in units of h bar. Right? This gives you the amount of this calculation. In fact, so this is really easy, right? If I said what's the spin would be the square root of 1/2 times 3/2 times h bar is equal to the magnitude of S, right? So I can actually calculate that numerically. That's a fixed number that the electron has. All right? But S sub z can have two quantum numbers. It can have m sub s. Well, it's always equal to m sub s times h bar, but m sub s can be equal to plus 1/2 or minus 1/2. Right? So there's two possible values for the z component. And we call these two different states spin up and spin down. So we call this one. So ms equals plus 1/2 equals plus 1/2 we call spin up. And the other one with m sub s equal to minus 1/2 we call spin down. Now, by the way, yeah, and of course this is with respect to WRT, with respect to the z-axis. WRT is my abbreviation for with respect to the z-axis. And again, we can ask the same question. what is the z-axis in space if I have a bottle of hydrogen atoms in this column? Right? I don't know. You want to make z this way, or do you want to make it this way, or do you want to make it that way? You decide. Right? Well, then, what direction is the spin? Well, we need a vector, an external vector, to define a direction. And so, just as we're going to talk about applying a magnetic field to define a direction in space, we can define a direction in space by the magnetic field that is generated from the nucleus. And we'll talk about that later. But the point is that there is a magnetic field that is caused by the nucleus, and that defines spin up and spin down. Because now, if I can have one electron, if it's doing its orbital motion around this way, and its spin vector is up, then I can have the other electron with its orbital motion this way, and spin is down. Right? So clearly, with respect to its orbital angular momentum, I can define up and down. Okay? So there are two spin states. Right? So there are now two values of m sub s for each value of L and m sub L. So the number of states for a given n is equal to 2 times n squared. All right? Because each one of those m L and m sub L states can have m sub s equal to plus 1, or m sub s equal to plus 1, or m sub s equal to minus 1. And m sub s stands for the z component of spin. M sub L stands for the z component of orbital angular momentum. Okay? So there's actually 2 angular momentums now to keep track of. It's orbital and spin. Same thing's true of the Earth's orbit, right? You have the orbital motion around the sun, and you've got the spin rotation around its own axis. Okay? So now I can have 2 electrons in the n equals 1 state. Right? I can have 2 electrons there because one of them I'm going to denote by spin up, and one of them I'm going to denote by spin down. Right? And the vector will just be the spin vector, which I'll kind of draw arbitrarily, but I'll draw it in 2 dimensions so that you can see the difference. Instead of, this and this way, I can't draw in the 3rd dimension to get the idea they're different, right? So that means that the n equals 1 state can have 2 electrons in it, and it's a filled shell. So every time we fill a quantum number, so a filled shell, or we could even refer to an unfilled shell, but a filled shell, a shell is one with with maximum number of electrons in it, with maximum number of electrons. Okay? So for the n equals 1, we can have 2 electrons. This is helium. Then we've got our first multi-electron atom. If I now go to n equals 2, then what I'm going to do is I'm going to start filling in the orbitals. The n equals 1 has 2 electrons, so it's already full. I'm going to go to the next shell, which is the n equals 2, and now I can have 6 electrons in there. So I'm going to put electrons in here, 1, 2, 3, 4, 5, 6. What are the angular momentums that they have? Well, I had said earlier that all angular momentum states have the same energy because the energy does not depend on L, right? But that's only for a single electron atom. Turns out that for a multi-electron atom, you can, the lower in general, not in general, but often, the usual case is that the lower angular momentum states get filled first. Right? That means that when I'm at the n equals 2 level here, so now these are at the n equals 2 for this outer shell, then I'm going to start and I'm going to fill the L equals 0, and then I'm going to fill the L equals 1. Right? Now, the reason is that people have worked out the details is that the wave function for the L equals 0 is closer to the origin than the wave function for L equals 1. That means that it has a closer distance in. It sees a higher charge due to the fact that it has less shielding from these other electrons and it's closer to the nucleus. And therefore, the lower angular momentum states are going to be more bound. They're going to be lower. So you're going to fill the lowest energy states first, starting with L equals 0. Right? It's just the way the wave functions worked out. That's also telling us something that the wave functions have a measurable reality. It isn't just that I can abstractly calculate the probability that electron will be 3 Bohr radii away from the origin, but I can use the wave functions to see which electron is going to be closer in and which one's going to be further out. And the ones that are closer in are more bound because they see a tighter charge. They see a higher charge. They're in a more bound state. Okay? So now there comes a point, and we'll discuss it a bit later, once you get into the 4s level, then there are actually cases where the 4s level gets filled before the 3D. Well, I didn't tell you about s levels yet. I'm sorry, I'm jumping ahead. Before the n equals 4, L equals 0 level does actually fill in before the last 2 electrons in the n equals 3 level. But usually this is the normal case. And you have to memorize the exception or you have to be given the sheet. And I told you, there's no memorization in this class, so anything you need to know is handed to you on a sheet. Okay? Everyone believes that right now. There's no memorization in this class. Good thing you don't take organic chemistry. It's 100%, almost 100% memorization. All right, so I'm glad I didn't take it, but I would have to take it. Okay, so everyone kind of get this concept. Now, I mentioned, was there a question? No? I mentioned earlier about the S and the P and the D. So I'm sure many of you have heard this before. Their S, P, and D are initials that refer to angular momentum states. So the S state is an L equals 0 state. The P state is an L equals 1 state. And the D state is an L equals 2 state. Right? And these are called orbitals. So we'll say, for example, the P orbital, let's say the 2p orbital is an electron in n equals 2, L equals 1. Right? And there's also another one here, which is FPDF. So F would be L equals 3. And we go on. This is simply nomenclature, but they are very frequently used. And I think in the back of CATS, certainly in Giancoli's book, the periodic tables give you where the last few electrons are, which orbitals the outer electrons are in, because they have a lot to do with chemical bonding, and the outer electrons are the most important when we're trying to understand how molecules form, right? But before we understand molecules, we have to understand atoms. So this is the scenario that we have. So in this case now, we can write out a nomenclature for this particular atomic configuration. This atomic configuration would be that for this particular atom, this would be equal to 2 electrons in the, the 1s is the 1s state. There are 2 electrons in the 1s state. There are 2 electrons. There are 2 electrons in the 2s state, and there are how many? Let's see. 1, 2, 3, 4, 5, 6. So we've got 2, 4, and then I've got 2 electrons in the 2p state. Right? So this gives me a total of, oops, I missed that up, didn't I? 4. 2, there's a total of 8 electrons. Right? So notice when I add up the exponent, quote exponents here, I get the number of electrons. So I have 2 electrons in the n equals 1, 1, 2, 3, 4, 5, 6, 6 electrons in the n equals 2. 2 of them are in the S state, 4 of them are in the P state. Once I get to 2p6 with 6 electrons, then that shell is filled. I now have the maximum number of electrons that I can have in the n equals 2 state and the n equals 1, which would be 10, right? 8 electrons, so 2n squared, so 2 times 2 squared is the number of states or electrons I can have for n equals 2, and then I can have for n equals 1, I can have 2 times 1 squared, so this is going to be a total of 8, right? Or 10. 10 electrons, right? That'll be 10 electrons, right? So where do these things fall on the periodic table? I don't have my pointer with me, so I'll use my arm pointer. Well, the general idea of the periodic table is that if there is only 1 electron in the outer shell, the last shell that has not yet been filled, then that's in a column 1 of the periodic table. If the subshell has been filled, it's usually, and by subshell, by the way, we mentioned filled shell, one with maximum number of electrons of a given, I left out an important point here, of a given n, or principal quantum number n, right? And the orbitals are also called subshells. So I can refer to this as the also called subshell. So when the angular momentum, and that's for a given value of L. Okay? So that's referred to the subshell. When those once a subshell is filled, it generally becomes an element in the last column over here, and those are called inert elements. Elements that will not easily chemically bind to other atoms. So they tend to be monatomic atoms quite frequently. Monatomic molecules. They're molecules in which there is only one atom and they don't bind to other elements easily. And those are in the last column, and it has to do with the fact that all the electrons in the last outer shell have been filled. There is no bonding. And we'll talk a little bit more about what does cause bonding, but the basic idea is that these are two extremes of the spectrum. Now, a common one, there are cases, and I'm going to mention one of them, which is called table salt, which is sodium chloride. So sodium has, looking on the periodic table, up here you can see the upper right number is 11, so it has 11 electrons. Chlorine has 17 electrons. Right? So if I'm talking about sodium then, I know that there's 10 electrons to fill 1s, 2s, and 2p. So the 11th electron must go to the 3s. Right? And so this has 3s1. So this is called a valence electron. It is the valence electron is the any electron that is in an unfilled shell. Or it could be filled shell too, but it's the last shell that has electrons populated. Okay? That's called the valence shell. Right? And the valence shell, which is the outer shell, is the one that dictates all the chemical properties for bonding of atoms to other atoms. Okay? So sodium has one valence electron. If we look at chlorine, for example, so chlorine has 17 electrons. Okay, so that must mean that this is certainly filled. So I have the 1s is filled, the 2s is filled, the 2p is filled, the 3s is filled, and this accounts for 12 electrons. So this would be 2 in this state, 2 in this state, 6 in this state, 2 in this state. These are 12, and the remaining 5 must go into the next state, which is 3p. So there must be 5 of those. So there are 5 valence electrons. Okay? There are 5 electrons in the outer shell of the chlorine atom. It only takes 6 for it to become a filled shell. Okay? So there's a strong affinity for an atom with one missing or one electron away from being filled. And so this, for example, will be the chlorine. And over here I have the sodium. And it only has 1 electron in its outer shell, right here. And when these two come close to each other, well, they can either share this electron, which means that it becomes what's called a covalent bond, or if the electron gets attached, we say attached, it means spends more time over here, and this chlorine atom then becomes negatively charged. This is Cl negative. The sodium atom just lost an electron, so it becomes sodium plus, right? And there's an electrostatic bond that's holding those two together. This is called an ionic bond. Okay. If they were equally shared between the two atoms, it would be called a covalent bond. Now, those of you that had chemistry, I must have heard this before, right? How many people have heard this covalent ionic bonds? Okay. Anybody has not heard? You haven't had it? Okay, okay. So anyway, this is the scenario that we have, and this is the way we interpret it. Similarly, we can expect that there will be molecules where, for example, well, there are other combinations that are possible. I'm trying to think of it using chlorine. Give me 1 second. No, leave it at that. But the whole idea is that basically, when you take an atom with a very small number of valence electrons and make it close to one that only needs 1 or 2 to get filled, those two are very likely to bond together, and they will either form the covalent or the ionic bond. That's the story. That's the story of electron spin. It's the story of the Pauli exclusion principle. It's the story of the periodic table. You do have problems that are involved. Do you have any questions before we go on? Yeah?
Are ionic bonds polarized?
Yes, they're polarized. Yes, they're polarized. So they're like this polar molecule. Remember the black body radiation? We said the molecules were made up of polar molecules. There's a molecular bond, but one of them is positive and the other is negative, and they're jiggling, right? And that jiggling creates the radiation, because oscillating charged particles emit radiation, just like electrons going up and down an antenna emit radio waves. Right? So that's the basic idea. Right? Any other questions on this? No? Okay. All right. Let's see. What else do we have? Well, before we go on any further, we should mention something about the energy level diagram. So you remember when we talked about the particle in a well, we talked about how to describe the total energy and the total energy and the potential energy. So we call this a potential energy diagram. I'm looking for my chart. There. So just as we did with the case of the square well potential, I can draw either the potential function or the total energy as a function of the distance r from the origin. And of course, the origin is where the proton is. And given what we know now, the potential energy function looks something like this. So the potential energy function U of r is given by minus ZE squared over 4 pi epsilon naught times 1 over r, right? This is the potential energy function for a point charge with charge ZE attracted to another charge. Okay, now, so what we can now look at here in terms of the orbital, in terms of the angular momentum is, or in terms of the energy, the quantized energy states that are allowed for hydrogen are down, the ground state is right here, is at minus 13.6 electron volts. And the next state up from there, n equals 2, so this is n equals 1. So this is n equals 1. And then up here, I will have n equals 2. And so here, the energy state will be minus 3.4 eV, which is minus 13.6 divided by 4, or 2 squared, for n equals 2. And this will be the energy state for n equals 2. And then n equals 3 will be up here, n equals 4 will be up here, n equals 5, and it will go on to infinity, except that the energies will only approach 0 as we go. And the binding energy, or remember we talked about, well, even on one of the exam problems, the minimum binding energy is the energy that it takes to liberate the most outer electron, right? So if I want to bring an electron into a region where E is greater than 0, so by the way, in terms of the black line, the red lines, this graph is plotting U or it's plotting E, right? E sub n, right? And E1, E2, and E3. This means that regardless of what the radius is, how far the electron is from the origin, it will have the same total energy. Whether it's a circular orbit, or it's an elliptical orbit, or it's no orbital at all. I mean, from a quantum point of view, all we know is the probability distribution. And we drew this last time, which is also in your handout. If we take the n equals 1, L equals 0 radial wave function, and we plot the square of that, R and L, or R squared, we'll call this R00 squared, then this radial wave function, by the way, we're going to multiply this by 4 pi r squared, which we have to discuss a little bit more, but this wave function squared looks something like this, right? And the most probable location is for A0 equal to 0.053 nanometers, which is what we call the first Bohr radius. First Bohr radius. But as you can see, the electron can be anywhere, right? This is a probability distribution. This is a probability. And this probability distribution means that it is possible for the electron to be anywhere in radius from 0 to infinity, right? This probability curve goes out to infinity. There's a probability that the electron in the atom of this projector is actually out here somewhere. That probability is 10 to the minus 98. Right? So realistically, we have to be within a few radii of the first Bohr orbit. But that's the basic point that I'm trying to make here. And this distance, as we fill up, so we can have 2 electrons in this state, we can have 8 electrons in n equals 2 state, right? So I can put my electrons in here. I can have, etc., right? Then I can have 2, 8, 18 electrons, n equals 3, and I fill them all the way up. This is another way of looking at how electrons populate the the atom in terms of their energy. Okay? So this is, again, just another example of an energy level diagram. Okay? Any questions? This stuff either must be really clear or really over your head. I think it's really clear, but you can let me know if it's not. Any questions? Okay. Okay. So there's one more topic that that I want to try to cover before our time runs out, and that is how to look at the angular momentum states of the what do we call it? The splitting of the energy levels due to angular momentum. So the splitting of the E sub n energy levels in hydrogen due to angular momentum L, right? Due to L. And up till now, we said in hydrogen, the energy level does not depend on angular momentum. The energy level only depends on the principal quantum number. Now, it turns out that if there's angular momentum involved, then I can have an effect that is observable that does depend on the angular momentum quantum numbers. Okay, and they are observable. They are, and this will be just described in the following way. First of all, what I will do is to say that let's imagine that we have a magnetic field with the magnetic field pointing up. So I have a north and south pole of the pole faces of two magnets, right? So we know that the magnetic field B is a vertical field basically up. This is B sub Z. Right? Within this magnetic field, now, I'm going to place the atoms of the hydrogen atom, and these will be in a gas discharge tube, as we've described before, so they will be able to be excited by collisions with the electrons coming from the tube, such as the tube I showed you last time. And I can describe the orbital angular momentum vector as following. Wait, let me make sure I've got the exact idea correct on here. And that is that, okay, so we're going to draw the orbital angular momentum as being a orbital angular momentum, which is an electron going around this way, which means that I now have the angular momentum vector going in the direction perpendicular to the plane of motion. And again, this is, of course, the orbital angular momentum. And I'm going to look for an interaction between the electron moving in the electric field, and I mean moving in the interaction between the electron moving in its orbit and the magnetic field. Okay, so there are some things that we should probably know or remember, and that is that this electron classically forms a current loop, right? This is a current loop. And what happens if I have, let's say, for example, a wire current? So I have a loop of wire in a magnetic field, and the effect of this magnetic field, and this is some current I carried in the loop. The effect of this magnetic field is to align or to twist or to rotate the current loop to be so that the angular momentum vector L is parallel to B. And that is what we call torque. And those of you that have ever studied or built an electric motor are familiar with the fact that the way electric motor works is that if you apply a current through a loop, then that loop will get torqued by the magnetic field, which is given by V cross B, and that begins to torque, and the loop begins to rotate, and right as it rotates over the top of the apex, the field going this way, the current switches in the loop, and it gets continued to twist around. And that's how an electric motor works, is that the current loop of wire acts in a magnetic field, acts to cause the thing to rotate. right? This is the opposite of an electric generator. Electric generator is one where you forcibly, with a crank, turn the loop and rotate the loop in a magnetic field so that it generates a current in the wire. And that was from Faraday's law, and that's how you generate electricity, is that you force the current to move. Either way, there's an interaction, and the interaction is a torque that causes it to align itself. Now, mathematically, what we do is we describe this as we describe this interaction U with, this is potential energy. So U is equal to the potential energy. And the potential energy for a loop of current in a magnetic field is given by minus mu dot B. Right? And remember, B is only in the Z direction. It's B sub Z in the K direction, so there's only one direction of the magnetic field. This is, and of course what this says is that the potential energy will be a minimum. Potential energy is minimum when mu is parallel, when mu is parallel to the magnetic field B. Now, we haven't defined mu yet. It may have been a while since you remember this in 273, but mu is equal to the current in the loop times the area. Right? So it's the area of the loop. So I have a certain area A in this loop, which I define by A. I have a certain current I traveling in the loop, and the product is called the magnetic dipole moment. The energy, the potential energy is minimum when mu is parallel to B, and that's of course when the net force acting on the loop is zero, and the object no longer has a force operating on it. It is like water running to its lowest gravitational potential. All right? But this is the interaction potential, and it is given by minus mu times the magnetic field. Now the reason why this is going to be important is because this quantity, which is the potential energy, we now want to calculate what is mu for an electron, what is mu for an electron, right, in orbit. In orbit. And it's in orbit, meaning that it has a certain current I that's generated by traveling a certain distance, 2 pi times the radius, in the orbital period time tau. So we imagine that instead of a macroscopic current, this is a single charge current, Q, and Q is the electron, and the electron is making one complete orbit revolution in a period tau, which is equal to 1 over the frequency, and 1 over the frequency can also be written as, I'm sorry, it's 2 pi over omega. Right? Omega is equal to 2 pi f, so that works out. Okay, right? So this is basically a microscopic current, right? This is a microscopic current. It is a very tiny current, but nevertheless, it's enough to produce a current, and therefore it has a magnetic dipole moment, and we can fill this out and say, okay, this is equal to by the way, we'll come back. I missed something here. Missing. This I is given by, I is charge per unit time. I'm sorry, this should be equal to minus the electron. It's charge per unit second. There we go. Current is in coulombs per second. So it's the charge of electron divided by the time it takes to go around. Okay. So now what we need to do is say, okay, well, mu is generated, so mu is generated or occurs because of I, and I occurs because of angular momentum, because of L, right? So mu and L must be related, and they must be very closely related. So let me write this out then, that mu is equal to I, so this is minus E over tau. There is the current I. The area of the loop, if it is a circular orbit, which is the one that we derived it for, is pi r squared. Okay, and this is one way. Okay, this is so this is equal to I times the area. Right? Now, tau, which we said was equal to 2 pi is equal to 2 pi over omega. So omega is the angular frequency, and so I can write this as minus E over 2 times omega times r squared. So this is a further reduction in the in the formula. So this is mu is equal to times omega times 2 pi over omega. Did I get that right? Yes. Is equal to r squared, and then I can combine this with L is equal to m r squared times omega. And if I combine these two together, then I get that the magnetic dipole moment of the electron is equal to minus 1/2 the charge of the electron divided by the mass times the angular momentum L. Right? So these two can be used to eliminate omega. In fact, I can eliminate omega r squared because I have it here. I have an omega r squared over there. And so mu, the magnetic dipole moment, is directly related to angular momentum. In fact, what we could do, we could replace this whole current loop with a magnet, this is equal to the, this side would be equal to, for example, the south pole. This side of the dipole magnet is the north pole, and then this magnet will twist away this way to line itself up. So this, of course, is a magnetic dipole because it is a bar magnet, and it will, in fact, torque or rotate so that the opposite poles align themselves up. In terms of current, it works the same way, and we're left with this result right here. Okay, we'll pick up from there on Monday or Tuesday and finish up, hopefully, chapter 42 on Tuesday. And so now you've got lots of homework that you can start working on and getting a head up on.